At first glance, Iapetus should be an ordinary moon. It orbits Saturn quietly, far from the chaos of the inner solar system. But when astronomers first observed it closely, they noticed something impossible. One half of the moon was bright and icy, the other half was almost completely black. Not slightly darker, not lightly stained, but dramatically different, as if two completely separate worlds had been fused together. From space, Iapetus looks like a cosmic two-faced world. One side reflects sunlight like fresh snow. The other absorbs nearly all the light that touches it. And that is only the beginning of its mysteries, because stretching across the entire equator of this strange moon is a massive ridge of mountains, a wall of rock running almost perfectly around the moon. Some peaks rise 20 kilometers high, making it one of the strangest geological features in the entire solar system. How could a moon develop two completely different surfaces? Why does it have a mountain ridge circling its equator? And what does this strange world reveal about the violent history of Saturn's moons? Tonight, we explore the mystery of Iapetus. Now, let's travel to one of the most mysterious moons of Saturn. In the 17th century, long before spacecraft explored the solar system, astronomers studied the sky with instruments far simpler than the telescopes we use today. The universe was still largely mysterious. Most planets were known, but their moons remained hidden to all but the most careful observers. Among those observers was a French-Italian astronomer named Giovanni Cassini. Cassini worked at the Paris Observatory in the late 1600s, and he was fascinated by the giant planet Saturn. Saturn was already known for its rings. Even through early telescopes, the planet appeared strange and beautiful. But Cassini believed there were still secrets waiting to be discovered around it. And in 1671, he noticed something unusual. While studying Saturn carefully, Cassini detected a small, faint point of light orbiting the planet, a moon. It was distant, dim, and difficult to see, but Cassini confirmed its motion. Night after night, Saturn had another satellite. He named it Iapetus after one of the Titans from Greek mythology. But almost immediately, Cassini noticed something strange. The moon did not behave like the others. Sometimes it was visible, other times it vanished completely. When Cassini observed Saturn on one side of the planet, Iapetus appeared clearly. But when the moon moved to the opposite side, it became almost impossible to detect. At first, Cassini thought the problem might be his telescope. Perhaps the moon was simply too faint. But the pattern continued again and again. Iapetus appeared on one side of Saturn's orbit and disappeared on the other. Cassini realized something remarkable. The moon itself must have two very different surfaces, one side reflecting sunlight strongly, the other side much darker, so dark that early telescopes could barely detect it. This was one of the first clues that Iapetus was not an ordinary moon. Centuries would pass before astronomers truly understood what Cassini had discovered. But even with limited instruments, he had already uncovered one of the strangest objects in the solar system. Today we know that Iapetus is the third largest moon of Saturn. Its diameter is about 1,470 kilometers. That makes it smaller than Saturn's moons Titan and Rhea, but still large enough to be considered a major satellite. Yet its size is not what makes it unusual. What makes Iapetus extraordinary is its dramatic contrast between light and dark. One hemisphere of the moon is incredibly bright, covered in clean water ice that reflects sunlight very efficiently. This side shines like fresh snow. The other hemisphere is completely different. It is covered in dark material, almost black in color. This region absorbs most of the sunlight that reaches it. The contrast between the two halves is so extreme that Iapetus appears like a cosmic yin and yang symbol. Astronomers call the dark region Cassini Regio, named after the astronomer who first noticed the moon's strange behavior. Cassini Regio covers most of the Moon's leading hemisphere. This is the side that faces forward as Iapetus moves through space along its orbit around Saturn. The bright areas, on the other hand, are located mainly on the trailing hemisphere. These regions are known as Roncevaux Terra and Saracen Terra. They are dominated by reflective water ice. But why does this difference exist? Why would half of a moon be dark and the other half bright? For centuries, this question puzzled astronomers. Early telescopes simply could not reveal enough detail. Even in the 20th century, powerful ground-based observatories struggled to explain the mystery. The true nature of Iapetus remained hidden. Then, in the late 20th century, spacecraft finally began exploring the outer solar system, and everything changed. One of the most important missions was NASA's Voyager program. Voyager 1 and Voyager 2 were launched in 1977. Their goal was to explore the giant planets and their moons. In 1980, Voyager 1 flew past Saturn. For the first time in history, a spacecraft approached the Saturnian system and captured close images of its moons. Among those targets was Iapetus. The images sent back to Earth revealed something astonishing. Cassini had been correct. The moon truly did have two completely different faces. The spacecraft confirmed that one side was covered with extremely dark material, while the other was dominated by bright ice. But Voyager also revealed something even stranger. Running directly along the equator of Iapetus was a gigantic ridge of mountains. This ridge stretched across more than 1,300 kilometers, almost the entire circumference of the moon. Some peaks reached heights of 20 kilometers. That is more than twice the height of Mount Everest. No other moon in the solar system has anything like it. The ridge gave Iapetus an unusual appearance. From certain angles, the moon looked almost like a walnut or a cosmic spinning top. But the spacecraft did not stay long. Voyager only passed by briefly. Its images raised new questions, but could not fully answer them. What created the dark material covering half the moon? How did the enormous equatorial ridge form? Why was the moon so different from Saturn's other satellites? These mysteries would remain unsolved for more than 2 decades. Then in 1997, a new mission was launched. A mission that would finally reveal the secrets of Iapetus. The spacecraft was called Cassini, named in honor of the astronomer who first discovered the strange moon. After traveling for nearly 7 years through space, Cassini reached Saturn in 2004. Over the next 13 years, it would explore the Saturnian system in extraordinary detail. And in 2007, the spacecraft performed a close flyby of Iapetus. For the first time, cameras captured high-resolution images of the moon's surface. The results were breathtaking. Iapetus truly was one of the most unusual worlds in the solar system. Its dark hemisphere looked like charcoal, its bright hemisphere looked like frozen snow, and the enormous ridge around its equator towered above the surrounding terrain like a colossal wall. The data from Cassini would transform our understanding of this mysterious moon. But to understand how such a strange world formed, we must look deeper, beyond the surface, beyond the ice and darkness, into the long history of the Saturnian system itself. Because the story of Iapetus began billions of years ago during the chaotic birth of the outer solar system. When the Cassini spacecraft finally sent back close images of Iapetus, astronomers were stunned. The strange pattern, first noticed centuries earlier by Giovanni Cassini, was not an illusion. The moon truly had two completely different hemispheres. One side was dazzlingly bright, the other incredibly dark. From space, the contrast looked almost unnatural. Half the moon reflected sunlight like fresh snow. The other half absorbed most of the light that reached it. The difference was so extreme that Iapetus became known as one of the most unusual objects in the solar system. But to understand this strange world, we first need to understand its motion. Iapetus orbits Saturn at a very great distance. much farther than most of Saturn's other moons. In fact, it lies nearly 3.5 million kilometers from the planet. That distance places it far beyond the large inner moons like Titan, Rhea, and Dione. Because of this distant orbit, Iapetus moves slowly around Saturn. One complete orbit takes about 79 Earth days, but like many moons in the solar system, it is tidally locked. This means the same side of the moon always faces forward along its orbit. Just as our moon always shows the same face to Earth, Iapetus always keeps the same orientation as it travels around Saturn. One side of the moon always leads the way. The other side always trails behind. And this simple fact turns out to be extremely important, because the leading hemisphere of Iapetus is the dark one, the region astronomers call Cassini Regio. Cassini Regio stretches across the front half of the moon. It appears almost black compared to the bright icy regions nearby. The surface here absorbs sunlight instead of reflecting it. As a result, the dark hemisphere becomes significantly warmer than the bright one. The temperature difference can be dramatic. During the long day on Iapetus, the dark regions may warm to around 130 Kelvin. That is still extremely cold by Earth standards, about -143 Celsius. But the bright icy regions remain even colder because they reflect most of the sunlight away. This difference in temperature plays a crucial role in shaping the moon's surface. But before scientists understood that process, they first needed to solve another mystery. Where did the dark material come from? At first, astronomers thought the dark surface might be the result of volcanic activity. Perhaps material from inside the moon had erupted onto the surface, but Iapetus shows no evidence of active volcanoes. Its interior appears cold and inactive. Another idea suggested that the dark material might have come from impacts. Meteorites striking the moon could have exposed darker rock beneath the icy surface. But this explanation also failed because the dark material on Iapetus does not appear to come from beneath the ice. Instead, it looks like something coating the surface from above. That clue led scientists to a new idea. Perhaps the material came from somewhere else in the Saturn system. In the outer regions of Saturn's moons, there are several small, irregular satellites. These moons orbit Saturn at unusual angles. Many of them are dark, rich in carbon-like material. One of these moons, named Phoebe, turned out to be especially important. Phoebe is very different from Saturn's larger moons. It likely did not form alongside Saturn. Instead, it may have been captured long ago from the outer solar system. Its surface is extremely dark, almost black, and as Phoebe and similar moons are struck by micrometeorites, they release tiny particles of dust into space over millions of years. This dust spreads throughout the outer Saturn system. Some of it drifts inward, and eventually it encounters Iapetus. Because Iapetus moves slowly along its orbit, the dust particles tend to strike its leading hemisphere. Just as insects strike the windshield of a moving car, the dust accumulates on the front-facing side of the moon. Over time, layer after layer of dark dust builds up on the surface. Gradually, the leading hemisphere becomes darker and darker. But this is only the beginning of the process, because once the dark material begins to accumulate, it changes the way the surface interacts with sunlight. Dark surfaces absorb more heat, bright surfaces reflect it, so the dark hemisphere of Iapetus becomes slightly warmer than the bright hemisphere. This temperature difference triggers a remarkable process. The bright regions of Iapetus are covered with water ice. When exposed to sunlight, some of this ice can slowly sublimate. That means it changes directly from solid ice into water vapor. The vapor then drifts through the thin environment around the moon. Eventually, it settles again, but it tends to freeze in colder regions, and the colder regions are found on the bright hemisphere. So over time, ice slowly migrates away from the warmer dark regions and accumulates on the brighter side. This process amplifies the contrast. Dark areas become darker, bright areas become brighter. It is a kind of thermal feedback loop. A small initial difference becomes larger and larger over millions of years until the surface becomes dramatically divided, half bright, half dark. This explains why Iapetus appears so striking when seen from space. The dark coating may be only a few centimeters thick in some places, yet it transforms the entire appearance of the moon. The bright hemisphere shines like ice. The dark hemisphere absorbs light and heat, and the boundary between them forms one of the most unusual landscapes in the solar system. But Iapetus still holds another mystery, because running directly along its equator is something even stranger. A gigantic ridge of mountains. A ridge so large that it circles the moon like a belt. Some peaks reach heights of 20 kilometers, far higher than most mountains found anywhere else in the solar system. This feature makes Iapetus look almost artificial, as if a massive wall had been built around the moon. For years, scientists struggled to explain how such a structure could form. Did the moon once spin much faster than it does today? Was the ridge formed by ancient volcanic activity, or could it be the remains of a collapsed ring system, similar to the rings of Saturn? Even today, the origin of this equatorial ridge remains one of the most intriguing puzzles in planetary science. And in the next part of our journey, we will explore that mystery in greater detail, because the strange ridge of Iapetus may hold the key to understanding how this extraordinary moon formed billions of years ago. When the Cassini spacecraft approached Iapetus in 2007, scientists expected to see craters, icy plains, and the strange division between light and dark terrain. But what the spacecraft revealed was something even more astonishing. Running almost perfectly along the equator of the moon, there was a gigantic ridge of mountains, a ridge so enormous that it stretches for more than 1,300 kilometers, nearly half the circumference of the moon. From space, it looks like a belt wrapped around Iapetus, a jagged wall of rock and ice rising above the surrounding landscape. Some peaks reach heights of 20 kilometers. That is more than twice the height of Mount Everest, and far taller than most mountains anywhere in the solar system. This feature is now known as the equatorial ridge of Iapetus, and it is one of the most mysterious geological structures ever discovered, because nothing quite like it exists anywhere else. Not on Earth, not on Mars, not on any other moon. Yet there it is, circling the equator of this distant world. From a distance, the ridge gives Iapetus an unusual shape. The moon appears slightly flattened at the poles and bulging along its equator, almost like a spinning top or a walnut. The ridge is not smooth or uniform. Instead, it is composed of a chain of mountains and ridges that vary in height and shape. In some places, the ridge appears as a single tall peak. In others, it splits into several parallel ridges. The slopes are steep, the sides drop sharply toward the surrounding plains, and many sections show evidence of ancient landslides where ice and rock have collapsed down the slopes over time. But the most puzzling question remains: how did this enormous ridge form? At first, scientists considered the possibility that it was created by tectonic forces. On Earth, mountains form when sections of the crust push against each other, but Iapetus is far too small and cold to support the kind of tectonic activity seen on our planet. Its interior lacks the heat needed to drive large-scale geological motion. Another idea suggested that the ridge formed when the moon was spinning much faster in the distant past. If Iapetus once rotated rapidly, centrifugal forces might have pushed material outward along the equator. Over time, that material could have hardened into a ridge, but computer models show that this explanation is unlikely. Even if the moon once rotated faster, it would not produce a ridge as tall and narrow as the one we observe today. A third theory proposed something far more dramatic. Perhaps the ridge is the remains of an ancient ring system. Just as Saturn has rings, Iapetus might once have had a ring of debris orbiting around it. Over time, the particles in that ring could have gradually fallen toward the surface. Because of gravity, they would tend to fall along the equator. As more and more material accumulated, it could have formed a ridge encircling the moon. This idea is fascinating, and many scientists consider it a possible explanation. But even this theory has unanswered questions. For example, what could have created such a ring? One possibility is that long ago, a small moon orbited Iapetus. Over time, tidal forces might have pulled that moon closer and closer. Eventually, the moon could have crossed the Roche limit. The Roche limit is the distance at which a large object can be torn apart by tidal forces. If the smaller moon crossed that boundary, it might have broken apart. The fragments would then form a ring around Iapetus, and over millions of years, those fragments could have slowly fallen onto the surface, building the ridge we see today. Another possibility is that a giant impact struck Iapetus in its early history. The collision might have thrown debris into orbit around the moon. That debris could have formed a temporary ring which later collapsed onto the equator. But even these ideas are difficult to confirm because Iapetus is extremely old. Its surface has been exposed to space for billions of years. Meteor impacts, erosion by micrometeorites, and other slow processes have gradually reshaped the landscape. The ridge itself shows signs of erosion and collapse. Large sections appear worn down compared to what they may have looked like when they first formed. Some parts of the ridge have broken apart. In other areas, craters cut through the mountains, revealing how ancient the structure truly is. Yet, despite billions of years of change, the ridge remains one of the most striking features on the moon. When sunlight hits the ridge at certain angles, long shadows stretch across the surface. The mountains stand out dramatically against the surrounding plains, and from space, the ridge can be seen from thousands of kilometers away, a colossal scar running across an entire world. But the ridge may also tell us something about the early history of the Saturn system. Billions of years ago, the region around Saturn was far more chaotic than it is today. Moons were still forming. Debris from the birth of the solar system filled the space around the giant planet. Collisions were common. Orbits shifted. Small moons may have formed, broken apart, and reassembled. In that turbulent environment, it is possible that Iapetus experienced events unlike anything happening today. A temporary ring, a destroyed moon, or a massive impact. Any of these could have contributed to the formation of the equatorial ridge. Today, the moon moves quietly through space. Its rotation is slow, its interior is cold, and its surface preserves the scars of ancient events. Yet the ridge remains a towering reminder of the moon's dramatic past. A structure so large, it reshaped the entire appearance of the world, and combined with the strange contrast between bright ice and dark terrain, it makes Iapetus one of the most unusual moons in the entire solar system. But the mysteries of Iapetus do not end there, because the ridge is only part of the story. The moon's surface, its craters, and its ancient ice hold even more clues about the violent history of the outer solar system. Clues that scientists continue to study today as they search for answers hidden in the frozen landscapes of this distant and extraordinary world. Among all the moons in the solar system, Iapetus may be the most visually striking. From space, it appears almost unreal. Half of the moon shines brightly in sunlight, the other half looks dark, almost like charcoal. This dramatic contrast divides the surface into two completely different worlds. The dark region is known as Cassini Regio. It covers most of the moon's leading hemisphere, the side that faces forward as Iapetus moves along its orbit around Saturn. This region is extremely dark compared to the surrounding icy terrain. In fact, Cassini Regio reflects only a small fraction of the sunlight that reaches it. Its surface appears deep brown or black, when seen by spacecraft cameras. For centuries, this dark terrain puzzled astronomers. Why would half of a moon be so dark, while the other half remains bright and icy? At first, scientists wondered whether the dark surface might come from the moon's interior. Perhaps volcanic eruptions once spread dark material across the leading hemisphere. But careful observations revealed no evidence of volcanic activity on Iapetus. The moon appears geologically quiet, its interior is cold, and its surface shows no signs of recent lava flows. Another possibility suggested that meteor impacts exposed darker rock beneath the ice. But this idea also struggled to explain the pattern. The dark material appears to coat the surface rather than originate from below it. Eventually, scientists began looking beyond the Iapetus itself. Perhaps the dark material arrived from somewhere else. The outer Saturn system contains many small irregular moons. These moons follow unusual orbits and often have very dark surfaces. One of the most important is Phoebe. Phoebe is a small moon that likely formed far from Saturn, perhaps in the outer solar system beyond Neptune. Long ago, Saturn's gravity may have captured it. Phoebe's surface is rich in dark carbon-like material, and over millions of years, micrometeorite impacts constantly strike its surface. Each impact throws tiny particles of dust into space. This dust spreads slowly through the outer Saturn system. Eventually, some of it drifts inward, and when it reaches Iapetus, something interesting happens. Because Iapetus always presents the same leading side as it moves along its orbit, dust particles traveling through space are more likely to strike the front-facing hemisphere. The situation is similar to driving through a rainstorm. The front windshield of a car collects far more raindrops than the rear window. In the same way, the leading hemisphere of Iapetus collects more incoming dust. Over millions of years, a thin coating of dark material builds up on the surface. At first, this coating may have been only a few millimeters thick, but even a small amount of dark dust can dramatically change how the surface interacts with sunlight. Bright ice reflects most sunlight back into space. Dark dust absorbs that sunlight instead. This difference triggers a remarkable chain reaction. The dark surface warms slightly more than the bright regions nearby. Even a small temperature difference can have powerful effects in the cold environment of the outer solar system. Iapetus is extremely cold. Surface temperatures can drop below -180°C during the long nights. But when sunlight reaches the dark regions, they warm slightly. That small increase in temperature causes something important to happen. The ice beneath the surface begins to sublimate. Sublimation is a process where solid ice turns directly into vapor without becoming liquid first. The water vapor escapes from the warmer, dark regions. It drifts slowly across the surface of the moon. Eventually, it freezes again in colder areas, and the coldest areas are found on the bright hemisphere. Because bright ice reflects sunlight, those regions remain cooler. So over time, water vapor leaves the dark areas and freezes on the bright ones. This process slowly redistributes the ice across the moon. The dark hemisphere loses ice, the bright hemisphere gains it. As more ice accumulates in the bright regions, they become even more reflective. As the dark areas lose ice, the dark coating becomes more visible. The contrast between the two hemispheres grows stronger and stronger. Scientists call this process thermal segregation. A small initial difference in surface color becomes amplified over millions of years. Eventually, the moon develops the dramatic two-tone appearance we see today. The boundary between the bright and dark regions is also fascinating. It is not a perfectly smooth line. Instead, it forms irregular edges where bright, icy patches extend into the darker terrain. In some places, bright ice fills the walls of impact craters. These areas remain cooler, allowing ice to accumulate. The crater floors may stay darker, while the crater rims appear bright. This creates beautiful patterns across the surface. Images from the Cassini spacecraft revealed these details in extraordinary clarity. Some craters appear almost like frozen islands of light surrounded by darker terrain. Others show streaks where ice has slowly migrated downhill over time. These features provide valuable clues about how the surface has evolved. They reveal that Iapetus is not entirely static. Even though the moon appears geologically inactive, subtle processes continue to reshape its surface over millions of years. Sunlight slowly redistributes ice across the landscape. Dust from distant moons continues to accumulate. Impact craters form when small meteoroids strike the surface. Each event adds another layer to the story of this unusual world. But Cassini ratio is not just dark. Its surface also contains complex textures and terrain. Some areas appear smooth, others show rugged hills and cratered landscapes. Large impact craters dot the region, some hundreds of kilometers across. These craters reveal that the surface is extremely old. Most likely, much of the terrain formed during the early history of the solar system, more than 4 billion years ago. Since then, Iapetus has remained relatively unchanged. Unlike Earth, it has no atmosphere, no weather, no oceans, nothing to erase the scars left by ancient impacts. The moon preserves its history in remarkable detail. Every crater, every ridge, every patch of ice tells part of the story. Together, they reveal a world shaped by both internal and external forces. Dust drifting through the Saturn system, sunlight slowly redistributing ice, ancient collisions sculpting the surface. And through it all, the strange division between light and dark continues to define the appearance of Iapetus, a moon with two faces, one bright as frozen snow, the other dark as cosmic shadow, and both telling the story of a world unlike any other in the solar system. Iapetus moves through space quietly, far from the busy inner regions of the Saturn system. This distant moon follows a slow and steady orbit around the giant planet. From the perspective of an observer standing on its surface, the sky would appear very different from anything we experience on Earth. Saturn would dominate the horizon, but unlike many of Saturn's other moons, Iapetus lies so far away that the planet would appear smaller in the sky than expected. Still enormous, still magnificent, but not overwhelming. The rings of Saturn would appear thin and sharp, stretching across the darkness like glowing arcs. The sunlight reaching Iapetus is weak. At Saturn's distance from the Sun, sunlight is about 100 times dimmer than it is on Earth. The world would appear permanently cold and quiet. Temperatures rarely rise above -130°C, even during the warmest parts of the day. But the environment on Iapetus contains another unusual characteristic. The moon rotates extremely slowly. One full rotation takes about 79 Earth days, and because the moon is tidally locked to Saturn, its rotation period is exactly the same as its orbital period. This means that a single day on Iapetus lasts nearly 3 months. For almost 40 days, the sun rises slowly above the horizon and remains in the sky for weeks. After that, darkness returns for another 40 days. These long cycles of sunlight and darkness play an important role in shaping the surface, because when sunlight finally reaches the dark hemisphere, it warms the surface slightly more than the bright areas. That extra heat drives the slow migration of ice across the moon. But the slow rotation of Iapetus also affects the moon's overall shape. Many moons in the solar system are nearly spherical. Gravity pulls their material inward, smoothing out irregularities over time. But Iapetus is different. Its shape reveals clues about its past. When scientists measured the moon's dimensions carefully, they discovered something interesting. Iapetus is slightly flattened at the poles, and it bulges slightly around its equator. This kind of shape usually indicates that a body once rotated faster than it does today. When an object spins rapidly, Centrifugal force pushes material outward along the equator. Over time, the object develops a noticeable equatorial bulge. But here is the strange part. The current rotation of Iapetus is far too slow to produce the bulge we observe today. That means the moon must have spun much faster in the past. Billions of years ago, Iapetus may have rotated in only a few hours. At that time, centrifugal forces could have stretched the moon outward along its equator. Eventually, tidal forces from Saturn slowed the rotation. The moon gradually settled into its current tidally locked state, but the shape created during its earlier, faster rotation remained frozen in place. The enormous equatorial ridge we explored earlier may also be connected to this ancient spin. If Iapetus once rotated rapidly, material near the equator might have accumulated differently. Some scientists believe the ridge formed during that early period when the moon was still hot and flexible enough to reshape itself. But regardless of how the ridge formed, it adds to the strange appearance of this world. Standing near the equator, an observer might see towering mountains stretching across the horizon, a colossal wall of ice and rock dividing the landscape. Beyond the ridge, the terrain would change dramatically. If you stood on the bright hemisphere, the ground would appear pale and reflective. Ice would dominate the landscape. Sunlight would scatter across the surface, creating a faint bluish glow. But if you crossed into the dark terrain of Cassini Reggio, the view would change. The ground would appear darker, almost dusty. The surface would absorb sunlight instead of reflecting it, and because of that, the temperature might feel slightly warmer, even though the entire world remains frozen. But Iapetus also reveals something else about the early solar system. Its surface contains large impact craters, some hundreds of kilometers wide. These craters formed when asteroids and comets struck the moon billions of years ago. In the early history of the solar system, impacts were far more common. Debris from the formation of the planets still filled space. Collisions shaped the surfaces of nearly every moon and planet. Iapetus preserves these ancient scars better than many other worlds, because it has almost no geological activity, no atmosphere, no liquid water, nothing to erase the marks left by impacts. The craters remain frozen in time. Some of the largest basins on Iapetus may date back more than 4 billion years. They formed during a chaotic period known as the Late Heavy Bombardment. During that era, the inner and outer solar system experienced intense asteroid impacts. Many of the craters on the Moon, Mercury, and other bodies formed during this time. Iapetus likely experienced the same bombardment, but because its surface has remained relatively unchanged since then, those ancient features are still visible today. Some craters have bright icy rims, others lie partially buried beneath dark material. These variations help scientists reconstruct the history of the Moon. By studying crater sizes and distributions, researchers can estimate how the surface evolved over time, and these studies reveal that Iapetus has been geologically quiet for billions of years. It is a frozen relic of the early solar system, a world where ancient processes are preserved almost perfectly. But even though the Moon appears inactive, subtle changes still occur. Micrometeorites continue to strike the surface. Dust from distant moons slowly settles across the landscape. Sunlight drives the gradual migration of ice. These slow processes operate over immense spans of time, millions of years, even billions. From our perspective, the world appears still, but over cosmic timescales, it continues to evolve. Iapetus reminds us that planetary worlds can change even without dramatic geological activity. Sometimes the most powerful forces are the slowest ones: sunlight, dust, gravity, working quietly, shaping the surface of a distant moon across the vast history of the solar system. And as we continue our journey through the mysteries of Iapetus, we begin to see that this strange two-faced moon is more than just an oddity. It is a window into the ancient past, a world that preserves clues about how moons form, how surfaces evolve, and how the outer solar system once looked billions of years ago. If you could somehow stand on the surface of Iapetus, the experience would be unlike anything on Earth. The ground beneath your feet would feel solid yet strangely fragile. Much of the surface is made of water ice, but at the temperatures found on Iapetus, ice behaves very differently from what we know on Earth. Here, ice is not soft or slippery. It is as hard as rock. Walking across the frozen terrain would feel like stepping across stone. The sky above would be completely black. There is no atmosphere on Iapetus, no air, no clouds, no winds. Without an atmosphere to scatter sunlight, the sky remains dark. Even during the day, the sun would appear as a bright star, much smaller than it does from Earth. At Saturn's distance from the sun, sunlight is weak, only about 1% as strong as the sunlight reaching Earth. Yet the sun would still illuminate the icy surface. On the bright hemisphere of Iapetus, sunlight would reflect strongly from the ice. The ground would appear pale and shimmering, almost like frozen snowfields stretching across the landscape. But if you travel to the dark hemisphere, everything would change. The ground would look dusty and dark. The surface would absorb most of the sunlight. Instead of glowing brightly, the terrain would appear shadowy and muted. The contrast between the two regions would be dramatic. Standing near the boundary between the bright and dark terrain, you might see the line dividing them stretching across the horizon, a frontier between two different landscapes. Yet despite the dramatic appearance, the environment of Iapetus would remain extremely quiet. Because there is no atmosphere, sound cannot travel. Even if rocks shifted beneath your feet, you would hear nothing. Silence would surround you completely, but the most impressive sight might be Saturn itself. From the surface of Iapetus, Saturn would appear large in the sky. Its rings would stretch outward in delicate arcs. The planet would glow softly with reflected sunlight, and nearby, other moons might appear as bright moving points of light. Titan, Rhea, Dione, all slowly orbiting the giant planet. Yet Iapetus itself is very far from Saturn. Its orbit lies nearly 3.5 million kilometers away. Because of this distance, Saturn would appear smaller than you might expect. Still magnificent, but not dominating the sky the way it does from Saturn's closer moons. But the view of space would be extraordinary. Without an atmosphere, the stars would shine clearly. Even during the day, the Milky Way would stretch across the sky like a glowing river of light. Countless stars would fill the darkness, the entire universe visible in perfect clarity. But life on Iapetus would face enormous challenges. The temperatures are brutally cold. Even in sunlight, the surface rarely warms above -130°C. During the long nights, temperatures can fall far lower. These conditions make the presence of liquid water almost impossible, and without liquid water, life as we know it struggles to exist. But scientists still study moons like Iapetus carefully, because even frozen worlds can reveal clues about the potential for life elsewhere. Many icy moons in the outer solar system contain subsurface oceans beneath their frozen crusts. Europa, a moon of Jupiter, is believed to hide a vast ocean beneath its icy shell. Saturn's moon, Enceladus, also contains a subsurface ocean which erupts into space through geysers of water vapor. These discoveries have transformed our understanding of where life might exist. Even in the cold outer solar system, hidden oceans could provide environments where life might survive. But Iapetus appears different. Unlike Europa or Enceladus, there is little evidence that Iapetus contains liquid water beneath its surface. Its interior is small and cold, and its geological activity appears to have stopped billions of years ago. Without internal heat, Any liquid water that once existed likely froze long ago, yet the moon still preserves valuable information because its surface has remained largely unchanged for billions of years. This makes Iapetus something like a time capsule from the early solar system. The craters, the ridge, and the strange contrast between light and dark terrain all preserve clues about ancient events. By studying these features, scientists can reconstruct how the Saturn system evolved over time. They can learn how dust travels between moons, how sunlight redistributes ice across a surface, and how early impacts shaped the landscapes of icy worlds. Iapetus also reminds us how diverse the moons of our solar system can be. Each one tells a different story. Titan with its thick atmosphere and methane lakes, Enceladus with its icy geysers erupting into space, Europa hiding a vast ocean beneath its frozen crust, and Iapetus, the strange two-faced moon with a mountain ridge circling its equator. Each world formed from the same primordial disk of gas and dust billions of years ago. Yet each evolved in its own unique way. The diversity of these moons reveals how complex planetary systems can be, and it raises an important question. If such strange and varied worlds exist in our own solar system, how many more might exist around other stars? Astronomers have now discovered thousands of planets orbiting distant stars. Many of those planets likely have moons. Some may resemble the icy moons of our own solar system. Others may be entirely different. Studying places like Iapetus helps scientists understand how moons form and how they change over time. It provides clues about the processes that shape planetary systems everywhere. And even though Iapetus itself may be frozen and silent, it still has a story to tell. A story written across its icy plains, its towering ridge, and its mysterious dark hemisphere. A story that began billions of years ago when the solar system was still young, and one that continues today as we explore the distant worlds orbiting the giant planet Saturn. When scientists first studied images of Iapetus sent by spacecraft, one feature stood out above all others: a giant ridge of mountains stretching almost perfectly along the moon's equator. It looked almost impossible. A wall of rock and ice rising dramatically above the surrounding plains. In some places, the ridge reaches heights of nearly 20 kilometers. To understand just how enormous that is, consider Mount Everest. The tallest mountain on Earth rises about 8.8 kilometers above sea level. The mountains of Iapetus can rise more than twice as high. Yet this ridge is not a single mountain. It is a chain of peaks and ridges extending for more than 1,300 kilometers, nearly half the circumference of the moon. Seen from space, it forms a narrow belt wrapped around the equator, and nowhere else in the solar system do we find anything quite like it. Scientists immediately began asking the obvious question: how could such a structure form? At first, the ridge seemed almost artificial. Some early observers even speculated about strange possibilities, but as scientists studied the images more carefully, they realized the ridge must be the result of natural geological processes. Still, those processes remain mysterious. One of the earliest explanations involved the rotation of Iapetus. Long ago, the moon may have spun much faster than it does today. When an object rotates rapidly, centrifugal force pushes material outward along the equator. Over time, this can create a bulging shape. Some scientists suggested that when Iapetus was still young, its interior may have been warmer and more flexible. Rapid rotation might have forced material toward the equator, forming a ridge, but this idea has problems. Models show that even a rapidly spinning Iapetus would not produce such a tall and narrow ridge. Instead, it would create a broad bulge around the equator, not a sharp mountain chain. Another possibility involves tectonic activity. On Earth, mountains often form when pieces of crust collide or shift, but Iapetus is far too small and cold for this kind of activity. Its interior lacks the heat needed to drive large-scale tectonic forces. Unlike Earth, the Moon has no moving plates. Its crust has likely been frozen solid for billions of years. Then there is the idea that the ridge formed from volcanic activity. Perhaps ancient eruptions along the equator built up the mountain chain. But again, the evidence does not support this explanation. The ridge does not resemble volcanic formations seen on other planetary bodies, and no volcanic vents or lava flows have been detected in the region. This leaves scientists with another intriguing possibility, one that sounds almost unbelievable at first. Perhaps Iapetus once had rings, just like Saturn. Imagine a ring of debris orbiting the Moon billions of years ago. Fragments of rock and ice circling above the equator. Over time, those particles might slowly spiral downward. Gravity would pull them toward the surface, and because the ring lay along the equator, the debris would fall along that same line. Gradually, material would accumulate along the equator, layer upon layer of debris, building up over millions of years, eventually forming a ridge. This theory gained support after scientists examined the structure of the ridge more closely. Some sections appear composed of multiple layers, almost like piled rubble. The slopes are steep, as if loose material collapsed downward after accumulating over time. In some places, the ridge even appears to have split into several parallel peaks. This could happen if falling debris formed multiple ridges before settling into a single structure. But if Iapetus once had rings, where did they come from? One possibility is that a small moon once orbited Iapetus. Over time, gravitational forces from Saturn might have destabilized that moon's orbit. Eventually, the smaller moon could have been pulled too close. When an object approaches too near a larger body, tidal forces can tear it apart. This distance is known as the Roche limit. Inside the Roche limit, gravity becomes so uneven that a moon can be shredded into fragments. Those fragments would then form a temporary ring system. Over time, the particles in that ring would gradually lose energy, and eventually they would fall toward the surface of Iapetus, depositing material along the equator. This process could create the ridge we observe today. Another idea suggests that a massive impact may have created the ring. Early in the history of the solar system, collisions between moons and asteroids were common. If a large object struck Iapetus, the impact might have thrown enormous amounts of debris into orbit. That debris could then form a ring, which later collapsed onto the surface. Both of these theories remain possible, but confirming them is difficult because the ridge is extremely old. Billions of years of impacts and slow erosion have altered its original shape. Large sections of the ridge show signs of collapse. Landslides have carried material down the slopes. Impact craters cut through the mountains, revealing how ancient the structure must be. Yet, even with this erosion, the ridge remains astonishingly large. It still towers above the surrounding plains, and it continues to challenge scientists trying to understand its origin. Some researchers believe the ridge may have formed through a combination of processes. Perhaps an ancient ring first deposited material along the equator, then later impacts and landslides reshaped the ridge into the structure we see today. Others suggest that internal stresses within the moon may have contributed. Even a small amount of internal heat early in the moon's history might have helped push material upward along the equator. The truth may involve several mechanisms working together. But regardless of how it formed, the ridge remains one of the most extraordinary features in the solar system. Standing near its base, the mountains would dominate the horizon, their steep slopes rising into the black sky, some peaks towering so high that their tops might remain in sunlight even when the surrounding plains lie in darkness. From orbit, the ridge looks like a scar across the surface of the moon. a reminder of powerful forces that shaped the world long ago. And combined with the strange contrast between light and dark terrain, it gives Iapetus a unique appearance. A moon that seems divided, half bright, half dark, and wrapped in a massive ring of mountains, a world unlike any other, orbiting quietly in the distant realm of Saturn. For centuries, Iapetus remained a mystery. Astronomers could see its strange pattern of light and darkness through telescopes. They could measure its orbit. They could estimate its size. But from Earth, the moon was still just a distant point of light. Even the Voyager spacecraft in the early 1980s could only capture brief glimpses of its surface. Those images revealed the dramatic two-toned appearance and the enormous equatorial ridge, but they left many questions unanswered. To truly understand this strange moon, scientists needed a closer look. That opportunity arrived with one of the most ambitious space missions ever launched, the Cassini spacecraft, named after Giovanni Domenico Cassini, the astronomer who first discovered Iapetus in 1671. Cassini was launched in 1997 and spent nearly 7 years traveling through space. Along the way, it used gravity assists from Venus, Earth, and Jupiter to gain the speed needed to reach Saturn. Finally, in 2004, Cassini arrived in the Saturn system. For the next 13 years, the spacecraft would explore the giant planet and its many moons. During that time, Cassini revealed incredible new details about Saturn's rings, atmosphere, and satellites. But one of its most exciting targets was Iapetus, because despite centuries of observation, this distant moon remained poorly understood. Cassini made its closest approach to Iapetus in September 2007. The spacecraft passed just 1,640 kilometers above the moon's surface. For the first time in history, cameras captured detailed images of this strange world, and the results were astonishing. The two-toned appearance of the moon was even more dramatic than scientists had imagined. The dark region Cassini Regio appeared almost black in some areas. Its surface looked dusty and rugged. Bright icy peaks occasionally poked through the darkness like islands rising from a shadowy sea. Meanwhile, the bright regions on the trailing hemisphere gleamed with reflective ice. These areas reflected sunlight so strongly that they almost appeared to glow. The boundary between the dark and bright regions formed a sharp contrast across the surface. In some places, the transition looked almost like a coastline, separating two different landscapes. But Cassini revealed something else about the dark terrain. The dark material did not appear to be very thick. In many craters, bright ice was visible beneath the dark coating. When impacts exposed deeper layers of the surface, the ice shone through. This confirmed that the dark material was likely only a thin layer covering the ice beneath. Cassini also studied the enormous equatorial ridge in unprecedented detail. The ridge was even more dramatic than Voyager images had suggested. Some peaks rose nearly 20 kilometers above the surrounding plains. Steep slopes dropped sharply toward the surface. In several places, massive landslides had carried debris down the mountainsides. These landslides created enormous fan-shaped deposits of ice and rock. The ridge itself varied in structure along its length. Some sections consisted of a single towering ridge, others split into multiple parallel ridges, and in some regions, the ridge appeared broken or eroded by ancient impacts. Yet, despite these variations, the ridge remained remarkably continuous along the equator, a colossal geological structure stretching across the moon. Cassini's instruments also measured the composition of the surface. Spectrometers detected large amounts of water ice in the bright regions, but the dark material appeared to contain complex organic compounds and carbon-rich dust. These materials are similar to those found on many dark objects in the outer solar system. This discovery strengthened the idea that the dark material came from outside, most likely dust drifting inward from moons like Phoebe, gradually coating the leading hemisphere. Cassini also provided important measurements of the moon's shape and gravity. These data help scientists understand the moon's internal structure. Iapetus appears to be composed mostly of ice with a small amount of rock. Its density is relatively low compared to many other moons. This suggests that the moon formed from icy material early in the history of the Saturn system. The interior of Iapetus is probably cold and inactive today. Unlike moons such as Enceladus, there is no evidence of internal heating or geological activity, yet the surface still preserves clues about events that occurred billions of years ago. Crater counts reveal that much of the terrain formed during the early solar system. Some of the largest impact basins may be more than 4 billion years old. These ancient scars tell the story of a time when the solar system was far more chaotic than it is today. Asteroids and comets frequently collided with moons and planets. Each impact reshaped the surface, leaving behind craters that remain visible even now. Cassini also observed subtle differences in temperature between the dark and bright regions. The dark terrain absorbs more sunlight and warms slightly during the long days. The bright ice reflects most sunlight and stays colder. These temperature differences help drive the slow migration of ice across the moon's surface. Over millions of years, water vapor moves from warmer areas to colder ones, gradually reinforcing the contrast between the two hemispheres. Thanks to Cassini, scientists finally had enough data to build a detailed picture of Iapetus. The mission transformed the moon from a mysterious dot of light into a complex and fascinating world, a world shaped by dust drifting through the Saturn system, by sunlight slowly redistributing ice, by ancient impacts that scarred the surface, and by geological processes that may have formed the giant ridge around its equator. Yet, even with all the information Cassini gathered, some mysteries remain. The exact origin of the equatorial ridge is still debated. The full history of the dark material remains uncertain, and many details about the moon's early formation are still being studied. But Cassini's exploration brought us closer than ever before. It allowed humanity to see Iapetus not as a distant curiosity, but as a real world, a frozen landscape of ice, shadow, and towering mountains, a moon that carries the memory of ancient events written across its surface. And even now, long after the Cassini mission ended in 2017, the data it returned continues to reveal new secrets. Each image, each measurement, each discovery helping us understand the strange two-faced moon orbiting far from Saturn, a world that once puzzled astronomers for centuries and still inspires curiosity today. Iapetus may appear quiet today, frozen, silent, almost unchanged for billions of years, but this stillness is exactly what makes the moon so valuable to scientists, because worlds that change slowly preserve their history. Every crater, every ridge, every patch of dark material on the surface of Iapetus records events that happened long ago. In many ways, Iapetus is like a cosmic archive, a place where ancient stories of the solar system remain written in ice and stone. To understand why, we need to travel back in time more than 4.5 billion years ago, back to the birth of the solar system. At that time, the sun had only just formed. Around it spun a vast disk of gas, dust, and ice. Within that disk, tiny grains began to stick together. Over time, those grains formed larger and larger bodies. Pebbles became rocks, rocks became asteroids. Asteroids merged into protoplanets, and around the giant planets, smaller disks of material formed as well. From these disks, moons were born. Iapetus likely formed within such a disk surrounding Saturn. At first, it was probably a chaotic environment, countless fragments of ice and rock orbiting the young planet. Collisions were frequent. Objects smashed together, broke apart, and merged again. Over time, gravity slowly gathered material into larger moons. Iapetus emerged as one of those early worlds. But unlike some moons, Iapetus formed far from Saturn. Its distant orbit kept it isolated from much of the activity happening closer to the planet. This isolation helped preserve its ancient surface. Many moons closer to Saturn experienced strong tidal forces. These forces can generate heat inside a moon, causing geological activity. Enceladus is a perfect example. Tidal heating within that moon drives enormous geysers that erupt into space. Its surface is constantly being renewed. Old craters disappear beneath fresh ice, but Iapetus lies much farther away. The gravitational pull from Saturn is weaker at that distance. As a result, tidal heating inside the moon is minimal. Without internal heat, the interior quickly cooled, geological activity slowed, and eventually the surface froze into the state we see today. This makes Iapetus a geological time capsule. Many of its craters formed during the earliest periods of the solar system, and because the surface has remained mostly unchanged, those ancient scars are still visible today. By studying the number and size of craters, scientists can estimate the age of different regions. Areas with many large craters are usually older. Regions with fewer craters may have experienced later changes. On Iapetus, most of the surface appears extremely old. Some terrain likely dates back more than 4 billion years. That means the moon preserves a record of the late heavy bombardment. This was a violent era when asteroids and comets bombarded planets and moons throughout the solar system. The Moon, Mercury, Mars, and many other bodies show evidence of this chaotic period. Iapetus also bears the marks of those ancient impacts. Some craters stretch across hundreds of kilometers. Their rims rise sharply above the surrounding plains. Their interiors remain dark and shadowed. Over billions of years, smaller impacts have struck the surface as well, each one adding another scar to the frozen landscape. Yet the most interesting part of Iapetus is not just its craters. It is the combination of several unusual features that appear nowhere else together. The strange two-tone surface, the enormous equatorial ridge, the frozen interior that preserves ancient terrain. These features make Iapetus unique among the moons of the solar system, and they help scientists understand processes that shaped many worlds long ago. For example, the dark material covering Cassini Regio provides clues about how dust travels between moons. In the Saturn system, small particles are constantly drifting through space. Impacts on distant moons like Phoebe throw dust into orbit around Saturn. That dust slowly spirals inward under the influence of sunlight and gravity. When it reaches Iapetus, it settles on the leading hemisphere. Over millions of years, this dust gradually darkens the surface, but the story does not end there. Because once the surface becomes darker, it begins to absorb more sunlight. This causes the ice beneath the dust to warm slightly. The ice then begins to sublimate. It turns directly into vapor, escaping into space. Some of that vapor eventually refreezes in colder areas of the moon, usually on the bright hemisphere. This process slowly moves ice from warm regions to cold ones, and it strengthens the contrast between the dark and bright areas. A small difference in color eventually becomes a dramatic division across the surface. Iapetus demonstrates how subtle physical processes can shape entire worlds, not through violent eruptions or massive tectonic shifts, but through slow changes driven by sunlight and dust. Understanding these processes helps scientists study other objects in the outer solar system. Many icy bodies experience similar effects: dust migration, temperature differences, gradual movement of ice across the surface. Even on distant dwarf planets like Pluto, similar patterns have been observed. Iapetus also provides insight into the formation of ring systems. The theory that its equatorial ridge formed from a collapsing ring may help explain how debris behaves around small celestial bodies. If confirmed, it would mean that moons can temporarily possess ring systems just like planets. Over time, those rings may disappear, leaving behind strange geological structures. This idea could apply to other moons as well. Scientists continue searching for similar features elsewhere because every new discovery adds another piece to the puzzle of planetary formation. Iapetus may not have oceans like Europa. It may not erupt geysers like Enceladus, but its quiet surface tells a different kind of story. A story about time, about how the solar system evolved, about how small changes can shape entire worlds across billions of years, and about how even the most distant moons can reveal secrets about our cosmic origins. When we look at Iapetus, we are not just seeing a strange moon orbiting Saturn. We are looking into the deep past, a frozen record of events that occurred when the solar system was young, a reminder that every world, no matter how quiet, carries a history waiting to be discovered. In the vast system of Saturn's moons, Iapetus stands apart, not because it is the largest, not because it is the most active, but because it is one of the strangest worlds ever discovered. A moon divided into light and darkness, a moon wrapped in a gigantic mountain ridge, a moon that seems frozen in time. For centuries, Iapetus puzzled astronomers. Even the man who discovered it, Giovanni Cassini, struggled to understand what he was seeing. Why could the moon only be observed from one side of its orbit? Why did it disappear when it moved to the opposite side of Saturn? The answer turned out to be one of the most unusual surface features in the solar system, a world where one hemisphere reflects sunlight brilliantly, while the other absorbs almost all the light that reaches it. But the story of Iapetus does not stop there, because this moon represents something much larger. It represents how the solar system evolved over billions of years. The strange appearance of Iapetus is the result of many processes working together. Dust drifting through the Saturn system, sunlight slowly redistributing ice across the surface, ancient impacts carving enormous craters, and possibly even a vanished ring that once surrounded the moon. Each of these processes left its mark. Each shaped the world we see today. Yet, even with everything we have learned, many mysteries remain. For example, the exact origin of the equatorial ridge is still uncertain. Did it form from a collapsing ring of debris? Was it created by internal stresses during the moon's early history? Or did several processes combine to build the enormous structure we see today? Scientists continue to study the ridge carefully. Computer simulations attempt to recreate how such a structure might form. Some models suggest that debris from a destroyed moon could have slowly settled along the equator. Others explore how rapid rotation in the early history of Iapetus might have contributed. But so far, no single explanation answers every question. Another mystery involves the dark material covering Cassini Regio. We know that dust from outer moons likely contributed to the dark coating, but the exact composition of that material remains under investigation. Spectral measurements suggest that it contains organic compounds and carbon-rich particles. Similar materials are found on many primitive objects in the outer solar system. Studying this material may reveal clues about the chemistry present during the formation of planets and moons. And then there is the deeper question: why does Iapetus exist in such an unusual orbit? Unlike most moons, its orbit is tilted significantly relative to Saturn's equator. This suggests that something in the early Saturn system may have disturbed its orbit, perhaps interactions with other moons long ago, or gravitational effects during the formation of Saturn's rings. The early history of the Saturn system was likely far more chaotic than it appears today. Moons may have formed, migrated, collided, and disappeared. Iapetus may be one of the few survivors from that ancient era, a relic of a time when the outer solar system was still taking shape. Even the surface itself continues to evolve slowly. Micrometeorites constantly strike the moon, tiny impacts that gradually reshape the terrain. Dust continues to drift inward from distant moons. Sunlight continues to drive the slow movement of ice from warmer areas to colder regions. These processes operate on timescales far beyond human lifetimes, thousands, millions, even billions of years. To us, the moon appears frozen, but in reality, it is still changing, just very slowly. Future missions to Saturn may one day return to study Iapetus again. More advanced spacecraft could map the surface in greater detail. Landers might even explore the ridge directly. Imagine standing at the base of those towering equatorial mountains, looking upward at icy cliffs rising kilometers above the plain, the sky black, Saturn hanging quietly in the distance, and the surface beneath your feet telling a story billions of years old. Exploring worlds like Iapetus reminds us how diverse our solar system truly is, from volcanic moons like Io, to ocean worlds like Europa, to icy geysers erupting from Enceladus. Each moon reveals a different chapter of cosmic history, and Iapetus tells one of the most unusual chapters of all, a story about dust drifting through space, about sunlight slowly shaping entire landscapes, about ancient rings that may have collapsed onto the surface, and about a world divided between darkness and light. Perhaps the most remarkable thing about Iapetus is how quietly it carries this story, orbiting Saturn once every 79 days, moving through the darkness, far beyond Earth, unchanged for billions of years, yet holding clues about the formation of moons, the movement of dust, and the evolution of planetary systems. When we look at Iapetus, we are not just looking at a distant moon, we are looking at a record of the early solar system, a frozen archive of events that happened long before Earth even had oceans. And perhaps that is what makes Iapetus so fascinating. It reminds us that even the quietest worlds can hold extraordinary secrets, worlds that seem simple at first glance, but reveal deeper mysteries the closer we look. And somewhere out there, beyond the orbit of Saturn, this strange two-faced moon continues its silent journey through space, half bright, half dark, and still keeping many of its secrets hidden among the stars.